This is my Lab 9 final project for ENME 351. For my project, I built a wind tunnel simulator to test the effect of flap deflection for maximizing lift. I'm currently in ENME 489F, which studies the dynamics of atmospheric flight. My motivation for this project was to put practice behind theory and simulate the significance of airfoil geometry with respect to lift and drag. The main part of my project includes an airfoil with a deflection flap. I used the coordinates from the NACA 4412 airfoil for its simple geometry, which allowed for easy design in SOLIDWORKS in terms of 3D printing and mounting. I was able to modify the geometry to produce this flap. I 3D printed a third part to mount the airfoil to a load cell, which allowed me to measure the airfoil's lift as air moves over it. For my final project in ENME 49F, we were required to write MATLAB code to calculate and graphically demonstrate how different airfoils and conditions impact various flight metrics. I was able to modify this code to import the data for the NACA 4412. This allowed me to visualize the various lift drag coefficients. And here I was actually able to calculate the drag coefficient based on the output polynomial value, which, as you can see, I incorporated into my code. First, I have manual mode, which allows the user to adjust the servo angle controlling the flap deflection by the potentiometer, and adjusting the potentiometer changes the flap angle displayed on processing in real time. In test mode, the last set servo angle in manual mode is used to measure and display the resulting lift-drag ratio, which provides insight into the airfoil's performance at a specific angle. As you can see, it's averaging around 3.5, which aligns with the graphical representation shown next. Next, in automatic mode, the system dynamically adjusts the flap angle to optimize the lift to drag ratio. The servo iterates through various angles and analyzes the lift force data from the load cell, and then ultimately lands on the angle that achieves maximum lift. The system pauses in between to make adjustments and ensure accurate readings. And as you'll see from the lift drag ratio, it outputs a value around 4.5. And this value aligns well with the MATLAB plot. Here is my Arduino code. First, I identified the library for the amplifier and declared my servo values from Lab 5. I incorporated the drag coefficients from my MATLAB code. I also set the scale as required for use of the library. Here I have each of my current modes listed and the functions within them. This is the string output for processing to visualize my data. Here is the lift to drag mathematical operation and my joystick functions. I also have my load cell initializer, also required for use of the library, and part of my optimization function, which scales the entire range. Here's my processing code. I first imported images of screenshots of my airfoil and flap from SOLIDWORKS and drew my boxes as well as moved the point of rotation for the flap image. Next, I made a function to show when a mode was selected and imported the inputs from Arduino. Here I have my cursor positioning, and this concludes my video recording for Lab 9. Thank you.